Okay, good morning. So let's start our fourth day of our school. And I have information for you. There is a change in the schedule. So the discussion panel in the afternoon will start at 2:30. Okay, not 2 o'clock, but 2:30. Okay. Okay, so let's start with the last lecture of Dr. James Jenkins.
Okay, thanks Marcelo. Okay, well, thanks again for coming. So, over the last three lectures, we've been kind of talking about discoveries of exoplanets, or how we can discover exoplanets, in particular small exoplanets, is where the field is really progressing now. And I think you're bored of hearing about correlated noise and things like that I've been kind of beating a drum about over these classes. So I'm going to move to a little more observation and speculation. Observation in the sense I'll show a few examples. I think showing examples is an excellent way to see where the field is at this moment and what we can do. And then I want to move a bit more to speculation in the sense of using Proxima b as a template for where we can go in the future, in the near future, and also asking the question, could Proxima b be habitable? And this is a good introduction for what we're going to talk about this afternoon. So I added these slides last night, kind of something particularly for the younger people, and me as well, to think about for Proxima b, and then use that for the future of these detections that we're going to get, or we believe we're going to get. So today we're going to ask the question, kind of those issues we discussed yesterday. How do we overcome them, and what do we get when we overcome them? And I said I'm going to show some discoveries that we've made. In particular, I'll show some that haven't been published yet, or at least one that hasn't been published yet. I'll let you see what we've been working on quite recently. And also, finally, I also thought it was important to finish on what's coming, particularly for young people making a way in this field. Where is our field moving to? What instrumentation's coming, both ground-based and space-based? And how do I see, or how kind of do we see the field developing because of that? And how is that going to really push the field forward? So, okay, so to start, using an American phrase, a bit out of left field, we've talked a bit about Jupiters, talked a lot about Jupiters actually, in particular hot Jupiters. And there was some results recently from Kepler by Wang et al. Just this year, that when we're thinking about habitability, I wanted to know, right, where could habitable planets be? Where could exo-Earths exist? In particular, we have a population of Jupiters. In particular, I said about 1% of stars have hot Jupiters. So that's Jupiters that we believe must have migrated from forming far, maybe 5 AU or so, beyond what we call the ice line, and getting themselves into orbital periods of a few days or so. And so the question then would be, could such planets or such systems have tertiary smaller planets in the habitable zone? They're kind of dynamically intense, we think, and potentially there's been some models that show that volatiles, water, etc., can be brought along, can be stirred up by this migrating planet. So potentially these systems could be interesting for habitability. However, when we look at the observations from Kepler, and we show here a period against the radius of the planet, and connecting systems that have tertiaries, so the multi-planet systems, when we do that, it turns out that basically the short period, the kind of hot Jupiters, don't really have any additional transits in the system. So they don't have any additional planets. And maybe that isn't a surprise given the dynamical nature of the formation or the evolution of that system. But when you get out to, let's call them warm Jupiters or so, then we tend to see other transits, additional planets in the system. So that's interesting in itself. Maybe at least a fraction of the hot Jupiters do have additional planets, but they're misaligned. So the systems could be heavily misaligned, and there's models for that. But that was just something to bring along that maybe we can discuss as well this afternoon. So we mentioned the habitable zone, and we talked. I thought I would show this graphic just to remember that we keep the habitable zone fairly simplistic. When we, at least for people like me who just look for these small systems, we try to parameterize it in a very simplistic sense. If we take a replica of the Earth, an Earth analog, place it around a star, at what distance could it maintain liquid water if it has a very similar atmosphere to the Earth? Very simplistic. And so this is what we get. We get this Goldilocks zone where it's too hot interior, it's too cold, and it's also means that's a function of stellar mass as well, in the sense that, again, we've got distance from the star in astronomical units against stellar mass, where one, of course, is set to be the Sun, a solar mass, and then you've got these small M-dwarfs that we keep talking about. And you can see this is why M-dwarfs are also beneficial for looking for habitable planets, that the habitable zone, or this classical habitable zone, moves interior, or moves closer to the star as a function of decreasing stellar mass. And to look at that more scientifically, how we do this, we tend to use these recent models that have been developed over the past 3 years by Koparapu, Dal, James Casting, etc. worked on these. And we see that basically we just get a parameterization of the incident flux on the planet. So this is just flux on the planet against the stellar effective temperature. So the Earth is set to be 1 in these units. And this is what we call the kind of classical habitable zone, or deemed the moist greenhouse, the classical habitable zone. Anywhere inside these two blue dashed lines, this is habitable no matter what the stellar mass. So you can see you're in the habitable zone no matter what. And the green, you can think of this as close to the continuous habitable zone. Remember I said that although stars are on the main sequence, they are still evolving, they're still changing, they're heating up as a function of time, very slowly, but they're still heating up as a function of time. So when you're in these types of regions, you're in what's known as the classical habitable zone, where you're always going to be habitable on the main sequence until the star evolves off the main sequence. And then there's kind of conservative limits as well. So in the red you see a recent Venus limit, so that's a kind of heavy greenhouse, and then you've got an early Mars out here in blue. And just to make a note that these are for cloud-free models. So these don't include clouds in the model, and clouds probably have quite a big impact or at least some impact on where these outer boundaries and inner boundaries should lie. Okay, so that's just a generic definition of how we see the habitable zone as observers, as exoplanet hunters, if you want to use that term. So I showed this on the first day. So I want to show some examples of systems that are interesting and are fairly new. And I really like GJ667c. It's a really interesting system in the sense that, as I said on Monday, it potentially has 7 low-mass planets. 7 little kind of super Earths, potentially rocky. Some of them in particular, this guy here, H, is incredibly low mass if proved to be real. We need more data to confirm this, hence why we put it in brackets here. But one of the points about this is this system's kind of really dynamically packed. It's really tight, all of these planets. And when we look and compare the distance, the semi-major axis, and look at those habitable zone models, we tend to find that we get 3 of those planets in the habitable zone for GJ667c. So this is kind of just a scaled down way of looking at the solar system, but we put boundaries of habitable zone, and in here we tried to add the effects of clouds. So I just said those things we're kind of cloud-free models, but you can add clouds and you can kind of broaden the horizons of the habitable zone. If you do that and you believe that this planet H is there, then it has 4 planets, potentially in the habitable zone. So these small systems, M-dwarfs, and we're learning from Kepler, from radial velocities, these M-dwarfs tend to be chock full of low mass planets, or small planets. And a lot of them tend to be packed, there's a lot of multiple low mass planet systems orbiting M-dwarfs. And for this, we can see that when that's the case, because of the dynamics of the system, and if there's a lot of small planets, small potential wells, they can happily sit fairly nearby to each other. And then when we look for habitable planets, single systems can have multiple objects that could be habitable. And that's excellent if we want to go on in the future and look for exo-life, because then we've got systems, benchmark systems, where potentially there's not only one planet to focus your study, but there's multiple opportunities for life to emerge in one system. And that's pretty cool. Also, this is pretty cool. I like these little mobile diagrams that were done 20 or 30 years ago for binary stars, and we extended them to planets. Quite nice. Anyway, that's an aside. So, I said I wanted to give you something new. Since I was commissioned here to give a few talks, I thought I would try and at least introduce a new result, something that's not published, and it'll let you see also what we're working on, and also the kind of systems dynamically that could exist or likely to exist here, in the sense that, so what I show is this is another small M-dwarf, GJ180, and what we've found is I've put B, C, that's because they're the kind of important ones for what I'm going to say now, but looks like there's a third planet also in this system already that we've got. So I show here, remember we talked about the periodogram, and the periodogram being the kind of like white noise or Gaussian. This is before we include red noise or so. And you can see that when you look at the periodogram, different colours are different instruments. So remember, we're not just focused on one instrument. We're trying to say that, okay, if we believe there's a system, a robust low amplitude signal, we should be able to see it, as long as we have the quantity of data, we should be able to see it in multiple instruments. And that's important, because it tells us if that is the case, if everything supports the data, supports the signal and supports the model, then we've got this extra level of confidence that these things are real. In the sense it's not just some kind of instrumental issue that we've not taken into consideration on one of these instruments. But one of the things is, we can look here, these dashed lines are the periods of those 3 detections. And so now you can see the difficulty in pulling out these small signals. This has over 100 data points, radial velocity data points, and from HARPS, which remember is 1 meter per second. And you can see that even in HARPS in black at the back here, because of the window function, because of the cadence, because we just hit this thing on a nightly basis, then we have to wait 6 months, then we have to wait 2 years if they don't award us more time and beyond, etc. Because of that window function, this periodogram gets really noisy, gets really multimodal, gets really ratty. And that's a good visualization of how difficult this is when we just consider these kind of Lomscargo periodograms and we forget about correlated noise and actually modelling the data in a more robust way. Because you can see when we come to our MCMC chains and we come to our Bayesian analysis and that model that I showed before, we pull out the 17-day signal where you can see it here. Now we do see it in the periodogram, it's there, but it's really clean in the MCMC. And so is the 24-day. That's fairly clean. There is a bit of interference here that you can see. So it's not as unique as we would like. And then there's this other strong high posterior probability third signal at 75 days that always comes up no matter how we run the chain, no matter where we start the chain. So that always comes up, so it's robust as well. but obviously nothing's as clean as this. And the interesting thing about this system is that these two planets, well, here's a visualization of the data. Now you can see why it was difficult when we just looked at the Lomscargo periodogram. When we look, this is the phased radial velocity that we've seen the first couple of lectures. And each of the different colours are those different data sets that I just showed before. And you can see that even the strong signal, I say strong, but even the primary signal is difficult to visually see. I mean, we're looking at here only 2.5 meters per second of radial velocity amplitude. 2.5 meters per second. So you can see it's difficult to see visually, and gets even more so as we go to these second and third order signals. Number one, that highlights the power we have in our detection, and that's a good thing. One of the other things about this system is the planet C here, that's a few Earth masses, it's likely to be a super Earth, but it's a few Earth masses, that falls nicely in the habitable zone of GJ 180. Number two, it sits at a 7:5 period ratio, so mean motion resonance, and that's a second order mean motion resonance. So every time this B planet, this planet here, orbits 7 times, this one orbits 5 times, and then there's a kind of interaction gravitationally. There's a resonance, but that's what it means, they're in resonance. And so that's interesting, because we've seen this come up again in a system we published around a sun-like star, and again it was small planets. But this again may be highlighting this importance of dynamics, that these small systems are quite dynamically packed. That's interesting. Anyway, that's aside. Keep that result under your hat for a few months. Okay, since we are discussing habitability, or going to discuss habitability, particularly, and have been, particularly this afternoon, what we really want to start to do as this field is to be looking at the constituents of the atmospheres of these small planets. That's what, when we talk about habitability of planets, one, things like these, what I'm showing are detections. That's what we do. We're trying to build a sample, but then we need to move beyond that, and we need to move beyond in the sense that we need to ask questions, do these planets have atmospheres, first and foremost? If they're just chunks of rock, well, this is a question that we should discuss maybe later. Are just chunks of rock, maybe even blocks of ice, is that okay? Do we need liquid water, is the question. How important is it to have liquid water, or to have an atmosphere in that sense? We should discuss that. But anyway, what we want to do is start to look at, if they do have atmospheres, what kind of atmosphere does it have, and what kind of constituents or the bulk properties of that atmosphere. And this is now quite a famous planet, GJ1214b, and it was found by transit around a nearby star, still a faint star, and it was followed up by HARPS and shown to be a legitimate small planet. And what they did then was, okay, we've got the transit, we know it's a small planet, genuine. Let's look at the transit, in and out of transit as a function of wavelength, which are these data points here, the stars and the filled circles. And this is what you see. You see basically it shows a flat spectrum from going at the optical all the way out to get into the near infrared. And it's very flat. And when you can compare that to various models, solar composition model without methane and just 100% water, and that's what it kind of agrees with. You can see that if you don't include methane, for instance, we get this heavy bump here, and also the solar composition model shows this heavy bump. It doesn't really follow the data in the red optical, get into the near infrared. So this is the kind of test I can say it's already being done on super Earths around M dwarfs. We want to push it down to not just super Earths if they're big fluffy balls, we want to get down to Earths. This is the goal. and we can try to perform these transmission spectra analyses and look for at least the bulk constituents of these atmospheres. Okay, so this year we released a discovery of Proxima b, and so I wanted to use it as a good way to look at how we can study nearby systems and how we can study these small planetary systems and use them as maybe test beds for what we can do in the future and how astrobiology can move forward as well in this sense. And so just to highlight, Proxima Centauri was discovered by a Scotsman actually back in 1915. That was nice for me to find out. It's the closest star to the Sun, of course. That's the big gain of finding a planet orbiting Proxima Centauri. It's only 4.2 light years away, which means we can even start talking about in situ observation, and I'll come to that at the end. A bit more speculative, but not as much as you would think. So one other point I should bring up is that we have already known its rotation period. Remember, that's really important, because if we worry about activity, we worry about that kind of modulation of the activity because of rotation. That was what we expected to be the biggest problem, but we had its period well known. It was already known, around 83 days. Of course, it's potentially part of a a trinary star system. So there's maybe more famous brothers and sisters, Alpha and Beta Cen, or Alpha Centauri and B. So it's the nearest star, and so we would think, well, surely there's a history behind planet search, and of course there is. So it was observed by Hubble, the faint object spectrograph, and Schultz in '98 published what looked like a detection, direct. So they were looking at a direct detection of a companion. And you can see here two images that they have, split by something like a month or so, month and a half. And they've seen a detection at about 7 magnitudes, something like that, fainter, at about half an AU. So in two images, they've seen this blob, this detection that they said was a companion, or they believed could be a companion, that's with a contrast that's something like 7 magnitudes fainter at half an arc second. However, when that was followed up with a wide field planetary camera 2 in 2000, it turns out there was no companion there, sadly, so it couldn't be confirmed. So that was a false positive. Something just to remember, this Proxima Centauri, being the closest star, has very high proper motion. And this was, I think, about 2 images taken something like 6 months apart or so, and you can see the background star differences because of its high proper motion. This thing's just whizzes by across the sky. It's really pretty cool. Okay, I discussed astrometry as well, and there's a future for astrometry in exoplanet searches, because we have an instrument called Gaia, a space telescope that's just been launched. I say just been launched, over a year now. And the first catalogue of data was just produced a month ago. So Gaia's going to remember the bias. It's going to help us look for big planets on wide orbits. But this kind of astrometric tests, particularly for stars like Proxima Centauri, there was works like Benedict et al. In '99 that used Hubble's fine guidance sensors to look for planets by the astrometric wobble. So remember, that's the wobble on the sky of the star because there's an orbiting planet gravitationally interacting. And this is the limits they got. Okay, so they couldn't reach, here's Proxima b, they couldn't really reach the habitable zone because of this bias. But they were able to rule out things like big Jupiters further out in the system. So if we look at the periodogram, you can see there's basically nothing there. There's this spike down at very low, which is just cadence issue that we see a lot. But there's nothing solid in the periodogram. And so, but the interesting point about this was that we now, at this point, we knew there's nothing big out in the system, or at least we had a good indicator that there's nothing large, a gas giant, quite far in the system. And also, and this was data we used actually in our detection, there was a published work by Endel and Kirster, and then they were on the paper, our discovery paper, because we utilised all their data to give us long baseline radio velocity, long baseline information, where we see the JD here, so time against the radio velocity, and they analysed that to look, and particularly in the habitable zone, they got very good constraints in the habitable zone. So this is the kind of sensitivity curves, period against mass. So it's sensitivity as a function of orbital period, where we go from 100% down to 25%. But even at 100% in the habitable zone, and this is where Proxima b lies, they were already down to about 3 minimum mass of 3 Earth masses already. So we already knew that in the habitable zone, Proxima b couldn't have anything fairly big. It couldn't have a really big, even super Earth by minimum mass. However, I wanted to show you that in their work, you can actually see the effects of Proxima b. Forget even that one. That looks like it's the first indications of the planet emerging. But I told you when you have a window function that's very strong, it's really difficult. And you can see, for instance, we see peaks like this at 1 year. So that's the 1 year alias, because the Earth orbits, of course, the Sun in 1 year. So these are the kind of things we need to remove. However, I said we utilised the data, which we did, and it was from UVES on the VLT, so that's an 8 metre telescope. It's the iodine cell method that we discussed on the first day. And Paul Butler took this back and reanalyzed, reprocessed the data. And when we do that and analyse it, you can start to see even more, including using our maximum likelihood methods, using our better modelling methods. You actually start to see the planet emerge even more out of that data alone. So with a bit more effort, they had a bit of bad luck in the sense that with a bit more effort, a bit more data, they could have really pushed for the detection of Proxima b many years ago. But that's the way it is. And so this just shows basically the data sets we used, and I'll explain these a bit more over the next few slides. But you can see that one of the points are that the signal is absolutely clear in our pale, we call it pale red dot data. That's what we dubbed the program, the pale red dot project. And the pale red dot project was, we conducted the observations this year in January and February. We took just over 60 nights of data where we observed Proxima b every night with HARPS. So every night we took a data point, and we ended up with something like 56 data points, so it was really efficient. And when you do that, that's what you see. Just in those 56 data points or so, you can see very clearly the signal. Now the good thing about that also is, when you look at the data that we had from before, and you look at the data that we get from the Pale Red Dot project, remember I said that spots in magnetic activity, they're not static, they're quasi-static. And what that means is that we don't expect to see signals continue with similar period, amplitude and phase over long time spans. It's quasi-static. So if we can break our data sets up and analyse them as independent data sets as a function of time, and we see that the period, the amplitude, the phase, for instance, is rock solid as a function of time, that's another level of confidence that this is not activity. And so here's our analysis, just to give you a look. This is again the delta log likelihood that we discussed in the first day, where we can see this is HARPS and UVES, but pre-2016. HARPS also went through an upgrade, so it's necessary to analyse data in this case pre-2016 and post-2016, let's call it, or at least post-upgrade, we need to analyse them independently because there's an offset in the data. And when we do that, well, one, you can see when you combine HARPS and UVEs pre-2016, already the detection is becoming quite clear. And the PRD data, it's clear. We detect it already. And then if you just combine the data together, what's nice is you can see that it's just basically additive. So we take the delta log likelihood of these two peaks, and it's just additive. So we then combine all the data, run the maximum likelihood again, and you get basically an additive log likelihood. It's stonkingly clear. This is as solid a result as we get in radial velocity analysis. And this is what the phase Doppler curve looks like. Just if I want to convince you visually. Where we've got our UVEs, HARPS pre-2016 and HARPS pale red dot shown here. And this lets you see that the signal is about 1.5 meters per second. So, as I said, well, this is the kind of domain we've been operating in. And it's the domain you need to operate in if you want to detect small planets in the habitable zones of M dwarfs. You need to be operating in the 1 meter per second domain at least. And we need to get below the noise in some cases. Okay, the HARPS noise here is really small. But we can see some of these data points are quite large, particularly from UVEs in the HARPS pre-2016 data. And when you do that, what you end up seeing is that Proxima B's got an orbit of about 11.2 days, a minimum mass of about 1.3 Earth masses. Remember, it's minimum mass again, just to keep making that clear. But it's got an equilibrium temperature of about 243 Kelvin. So throw on Earth similar, or at least a tenuous atmosphere around that, and then you can maintain liquid water on the surface. That's the point. Yep.
How do you get the estimate for the equilibrium temperature?
No, it's estimated basically by the irradiance of the star in the distance. Yeah, that's it. Very simplistic. I won't go through all of these slides again. We went through them yesterday to look at the effects of flares and photometry on the data, and I just wanted to highlight that was actually the data we discussed yesterday was for Proxima B, and to make it clear that we also observed photometrically for 60 days. So it's quasi-simultaneous photometry with the radial velocities, and that was another key point of how we could decorrelate the data. Just to finish up discussing flares, I wanted to show you that we actually did detect flares in the spectra of Proxima B, in the HARPS spectra. So this is the H-alpha equivalent width, and the sodium line equivalent width, sodium D1, D2, and the calcium HK flux. And each of these three shows big deviations. When you look at the radial velocities, it doesn't have a huge impact on the RVs. That's an important point for us, because a lot of these M dwarfs are flaring. They're quite active stars. But the good thing is, maybe it's not hugely important, really detrimental to look for exoplanets, small exoplanets. Okay, so let's change tack a bit, and this is what I added last night. This is work I had nothing to do with, but it's important for what we're going to discuss later, and what we've been discussing this week, in the sense that we say Proxima B is a terrestrial, let's call it a terrestrial mass planet in the habitable zone of the nearest star to the Sun. That's great. That's a lovely thing to say, and gets you a Nature paper, etc. But the question is, the real point is, that we would like to know is, how habitable is Proxima B? And can we understand, we can at least put a probability on Proxima B being habitable. Now, this paper came out by Barnes straight after our discovery, where they tried to look at various indicators of habitability. And so the reason I put these slides up, one is for that reason. This maybe give us things to think about, to discuss this afternoon. One of them being, so if Proxima Centauri is bound to alpha Centauri and Beta Centauri, or it's part of that system, it's proposed that that system was born closer to the galactic centre. And so it migrated through the galactic potential and migrated past, let's say, many more stars. So it's going through a potential, the galaxy, that's got spiral arms, etc. So there's other things going on. And it's also bound to another 2 stars, gravitationally, possibly. I mean, as an observer, I say possibly, only because some people still don't believe that Proxima Centauri is bound to Alpha and Beta Centauri, because it's incredibly wide. In fact, the orbital period has had limits on it of great, or at least a minimum orbital period of 500,000 years. So they're really, really wide orbiting. The problem for me is that they have to be bound in the sense that they're at the same distance and they've got the same proper motion, etc., spatial motion, the same radial velocity. So they have to be, for me, they have to be bound. They're in the same spatial, how would we say it, spatially close, nearby. So anyway, some people still don't believe they're bound. But we can look at, you can make models of the galactic potential and look at how that system evolved from over billions of years. With these dashed lines being the age now, it's about 4.5 billion years, very similar to the Sun. So the point is, one of the points are that as this system's evolving, and you've got Proxima Centauri also orbiting Alpha and Beta Centauri, then a number of the simulations showed that close passages of Proxima, just to even our siblings, as you're going through this galactic potential, could disrupt the system. In the sense that you've got these massive, large oscillations in eccentricity, and it takes, in this simulation at least, it took a long time to basically get incredibly high and say that this is maybe gone. If it didn't settle, how is Proxima B going to feel anything from Alpha, etc., Centauri, if the orbit that Proxima Centauri is on and in the system is 0.9 or above? And that's what the simulation there is saying could be the case. So one point for us is just to think that also there's evolution through the galaxy over long timescales. And how does that affect, particularly if you're part of, let's say, a trinary system or a binary system, how does that affect planets or planetary systems? So that's something to think about. Another study they made was looking at the eccentricity evolution as a function of time, particularly because I never mentioned that we discovered Proxima B, but we also discovered 2 other signals in the data. Now, they're not significant enough that we could publish them. In fact, they're not even unique. The main signal runs from constraints of about 40 days out to about 500 days. So it's completely unconstrained because it's so small. But there's a potential there that there's at least a second small planet orbiting the star that's already manifesting in the data. So Barnes et al. Took what we published, assumed 250 days or so, and then looked at the dynamics of the system. So you can see here time in billions of years, and if you don't have an outer planet, so you've just got Proxima B, it's not affected tidally, it's not affected gravitationally by an outer planet, then you quickly circularise the eccentricity, or its orbit, even if you start at, well, moderately high. You quickly, after a couple of billion years, you're down at an eccentricity of 0 or so. However, if you put another planet exterior out at, in this case, they simulated 250 days or so, and you look at how it interacts if Proxima B has kind of some eccentricity, particularly here it's this moderate eccentricity of 0.2, well, what they make the claim is that Proxima B's orbit then takes a long time to circularise. So they make the case that Proxima B maybe is not on a circular orbit. It's on an eccentric orbit. Eccentric orbit in the sense that our radial velocities were able to put a constraint on the eccentricity, but not a very good constraint. Not a very good constraint. We could only constrain it to about an eccentricity of, it has to be less than about 0.35. So we couldn't say it's circular. It's probably it's circular, but the upper limit we've got is 0.35 in eccentricity. And the question is, if that's the case, if there's another planet that could potentially maintain a high eccentricity or a moderate eccentricity over long time scales, so how does that affect the presence of, or habitability, the presence of life on a planet, where the planet comes close to the star, sweeps out further from the star? We've seen gas giants that do this. Much more extreme cases where you're getting thermal shocks and stuff on the upper atmosphere of the planet as it passes really close to the star. But how does eccentricity affect habitability, basically? That's the question. So that's, again, something we can maybe discuss later this afternoon. And remember yesterday, we talked a bit about stellar evolution, kind of stellar evolution. So we've heard how stars form. They get on the main sequence, but they're still evolving. But particularly in that early phase, stars, well, first we can see evolution of let's explain this. We've got time in years against orbital distance, where we're showing the evolution of the habitable zone as the star's beginning to heat up, as it's making its way to the main sequence, Proxima. And remember, we see that these things just have straight Hayashi tracks. They just go all the way, like, straight down onto the main sequence. And what this shows, depending on where you put your limits, this is the orbit of Proxima b, it's a function of time, and this is where we've got this classical habitable zone. But it shows that early in the evolution of the system, the habitable zone was much closer to the star. In the sense that, remember that the disk goes really fast. We've said, what, 5, 10 mega years, whatever you put that as being disk lifetimes. So Proxima b, unless it's interacting with other planets, or maybe with the potential from Alpha and Beta Centauri, but those are incredibly wide. So that's very unlikely. Proxima b got to its orbit fairly rapidly, fairly fast in this sense. And it got there, probably could be long before the habitable zone had reached its orbit. In the sense it took about 160 million years for the habitable zone to reach Proxima b's orbit here. So when we consider that, what impact did that have for it, particularly the early delivery of water on Proxima b? So that's a question that's interesting. Keep that in mind. The early evolution, if you're already in the orbit, in the habitable zone, and it can take 150 mega years before it reaches your orbit, and you've been stable there for 150 million years. What does that do what does that say for the potential for Proxima b or these other planets potentially to have liquid water on their surfaces? Remember, I'm discussing it in the search for liquid water. Another study that came out quite quickly after was from Ribas et al. That wanted to look at the basically tidal locking. So this has been kind of touted in the field as problematic for planets in the habitable zones around M-dwarf stars, in the sense that they're expected to be tidally locked. So from tidal dissipation, you end up with this is the Earth-Moon system, why we see the same face. And so the discussions that go on in the field are that this happens quite rapidly, or thought to happen quite rapidly, when your planet's very close to the star. And so if Proxima b is tidally locked, then what effect does that have on habitability? Well, but Ribas looked in another way. They also looked at the triaxiality, or kind of the gravitational torque on a non-axis symmetric system. So basically if it's eccentric, that's what they're looking at. Because we said, remember I just said to you, the radial velocities, we have our upper limit at 0.35. And so Proxima B can have any eccentricity in this range at all, from radial velocity constraints. And so what they looked at was, well, if you've got an eccentricity of 0, then probably you're tidally locked. That's what they're saying. But if it has some moderate eccentricity, there's a kind of probability that you can be caught in a potential that gives you a 3-to-2 resonance, or rotation. So you're not actually fully tidally locked in the sense that you've got one face facing the star at all times, but you've got a 3-to-2 resonance with your rotation. So you're kind of slowly also spinning. So the whole, what I mean is the whole planet gets to see the star over time. So you're not tidally locked in that case. And whether that's good or bad depends on if we believe that tidal locking is problematic. And that, there's various ways around that. There's various things we need to understand, in particular is the atmosphere. Because if we can set up winds or so in the atmosphere, if Proxima B has an atmosphere, right? This is one of the big questions. Does Proxima B even have an atmosphere? But if it does, and even if you're tidally locked, then the question is, what do winds play, or heat redistribution? So if we just take it as a chunk of rock with nothing else on it, then we say, okay, well, one side of that is completely irradiated and stiflingly hot, and you get to a region in the centre where you take a little step and it's cold, and right on the other side it's frozen cold. However, even in that case, then you've got at least a ring around the planet that would have a moderate temperature. But the question of tidal locking is something to discuss, and tidal locking in the presence of an atmosphere as well, so heat redistribution. And so, just at this point about tidal locking, I wanted to come and say that looking at the habitable zone, there's also other parameterizations of the habitable zone. I say other parameterizations, we can look at it as a function of mass, of planetary mass, where we can see that, for instance, slightly more massive planets, so super-Earths, like these 5 Earth mass planets, potentially can sustain liquid water, or sustain habitability, if that's what we're going to say. They're a bit more, there's a wider parameter space compared to smaller planets. They're more robust as far as maintaining liquid water on the surface happens. And also that, so I say here that the differences in the inner edge of the habitable zone between dry, tidally locked planets and wet or water worlds is different, and we can see that. So there's a dependence on from tidal locking between also just land covered and water worlds, and those are the kind of two extremes. So maybe if it's more, these planets are more Earth-like, where you've got some mixture of land and water, that kind of thing is maybe, should we say, more likely, if we've even got water at all on the surface. I want to be clear though, being an observer, remember, at the moment we have no idea if Proxima B has an atmosphere at all. So at the moment, we've got a minimum mass, an orbital period, and a constraint on an eccentricity. That's what we've got. We don't have an idea yet if it's got an atmosphere or not. Just to kind of make that clear. But if it did have an Earth-like atmosphere, some kind of tenuous atmosphere, we can also look at the effects of the radiation. So remember, I said Proxima B is quite active. Proxima Centauri, sorry, is quite active. The star's fairly active, and it's got outbursts, these flaring events, etc. And what you can do is you can look as a function of time at basically hydrogen loss. And you can create these various curves from various different models and look at the amount of hydrogen that we expect to lose from any tenuous atmosphere that Proxima B could have. And when you do that, and when you compare it to more like an Earth-like atmosphere, you find that, or at least Ribas et al. Found that it could only have lost something like 1 Earth's ocean's worth of hydrogen. So what that's trying to say is that irradiation from Proxima b and outbursts from the flares are not detrimental to maintain liquid water or to maintain water on Proxima b or in the atmosphere. And what it's trying to say also is that if it has an atmosphere, it shouldn't be gone after 4.5 billion years. If it's got a tenuous atmosphere, it should still maintain that tenuous atmosphere. So it shouldn't be stripped of its atmosphere. And that's an issue because planets that we've already found, particularly gas giant planets, like HD 209458b, which was the first transiting gas giant, or the first transiting planet, that was found to have some kind of like cometary tail. So there's the upper atmosphere is being basically evaporated, it's being blown off as it goes round. So that was a worry, let's say, if for habitability of planets around M dwarfs where they're so close to the star, and the stars are generally they're quite, or at least a high quantity of M dwarfs are active. But in Proxima's case, if it has an atmosphere, it should still have it. It shouldn't be blown off after 4.5 billion years. And that's a good thing. Okay, Barnes et al. This is getting, should we say, kind of more speculative, but it's simulations of Proxima b. And they run simulations of atmospheric oxygen pressure against the final water content to try and place versions of Proxima b or versions of planets around it in the habitable zone with similar characteristics to Proxima b and Proxima Centauri, where if you simulate the system, where can you look in the future to find, I mean, if we could observe water content and atmospheric pressure, we can prove it's got an atmosphere, so we're going to follow up with transits, hope that it transits. If it transits, then we can start probing the atmosphere, if it has one. But if you give it an atmosphere in some case anyway, you can start looking at what we would expect in water content and final atmospheric oxygen for habitability. And in this case, when you've got inefficient oxygen sinks, what they found was that you get habitability in this region here of for water content, quite high water content and low final atmospheric oxygen. And then you get some false positives for habitability and false positives for uninhabitable here. If you can increase the oxygen sinks, so you can kind of hold the O2 on the planet, then you can really extend the habitability or the potential for liquid water on the surface. This is getting more speculative now. I want to keep stressing, we don't know if Proxima b has an atmosphere or not. So the conclusion that you get after going through these tests, now this is excellent for us to discuss in this meeting, but for Proxima b, the conclusion is that it may or may not be a suitable place for exolife. That's basically what you get as scientists out of that. So this is a summary of Proxima b, but let's put in red, for the time being, it's a genuine exo-Earth. I don't know, I say a genuine exo-Earth. It's an exo-Earth if it has a small, if its minimal mass is close to its absolute mass, and it has an atmosphere, a small, tenuous atmosphere. But more data is needed. Proxima Centauri is the nearest star to the Sun. So let's start thinking a bit more outside the box now. It's only 4.2 light years away, nearby. So what about observing Proxima b in situ? And normally, and I can see some people already sniggering at this, but we're getting beyond laughing about that. If we're at hundreds of parsecs, then we can have a good giggle. But when we're talking at 4.2 light years away, now, okay, New Horizons would take 80,000 years or so. That's quite a long time. But there's initiatives now that want to send craft, in this case very, very small craft, riding beams of light, breakthrough starshot for instance, where if the technology can be developed, it's expected that these craft will reach Proxima b, or Proxima Centauri and Alpha Centauri, in only 20 years. So maybe, for the first time in history, we're at a point where we can actually believe that before we're all rotten in the ground, we might actually have images of Proxima b, of a planet in the habitable zone, from in situ. And that's pretty cool. So check out the Breakthrough, or keep an eye on the Breakthrough Starshot project. Okay, so let's change tack for the final 20-25 minutes. So we've talked about Proxima b, and that's a lot of... we looked at a lot of things to discuss as far as maintaining liquid water, habitability, that we can discuss this afternoon. But I wanted to just finish up on the kind of future of this field, where it's going, where I see it going, and where we're trying to drive over the next 10, 20 years. And we talked a lot about stellar noise yesterday, and stellar noise sources. And so I told you that activity has a chromatic dependence. So for instance, if we just discuss spots, you've got a spot in the photosphere, and if in the optical, that spot has a much higher contrast than it does if we observe the star, in the near infrared, for instance. It's got a higher contrast. And if it's got a higher contrast, that means for radio velocities, for photometry, it has a higher impact. It's noise that it'll inject into your observations is higher. So what you can do is to look at signals both in the optical and in the near infrared and compare, because they should be the same. For instance, a Doppler signal, that doesn't care about wavelength. We should get the same amplitude in the optical as we do in the near infrared. So this was a proposed planet by Satayawan, still is a candidate, I guess. But you can see the amplitude in the optical, this was from Pharos, is a couple of 100 meters per second. But then it was followed up by Fujihara in 2010, just a couple of years later. I mean, we're getting pretty sparse here, especially if these error bars are a bit larger. This is from CryRes on the VLT. That they found actually the signal can only be about 50 or so meters per second in the near infrared. So now this looks like a genuine false positive in the sense that we look in the optical and get something 200 meters per second, then we look in the near infrared and the amplitude of the signal goes down by a factor 4. So this looks like a genuine signal from an active star, and the star is active actually. It's a fairly young star. I think this, is it right, TW Hydra, I think this might be. Yeah, it's TW Hydra. So this is an active star, and you can see it's a short period as well, 356 days. And so that's what we need to be careful about. But the good thing is we can develop instrumentation now if we can observe that, or simultaneously observe in the optical and the near infrared. So keep that in mind. That's where we're going. But so the thing is, what I'm saying is the near infrared can be important to rule out false positives if we can simultaneously observe in both bands. So this is where one part of the field's going. It's going to develop methods to search for planets in the near infrared robustly. And that comes down to developing precise rulers. And we were working on this when I was at Penn State actually, and where I'm going to say this is what we're going to use as rulers for the future. The laser frequency comb. We'll get to that in a second. But in the near infrared, you can also try to move away from thorium-argon lamps. And it turns out uranium neon lamps are pretty stable, and they've got a lot of lines in the near infrared. And so these things turn out to be quite good. If you look at the standard deviation, we'll see what the laser frequency comb is in a moment, but you look at the standard deviation from the laser frequency comb and the uranium neon, okay, it's not too bad. And we can look at the difference between the two. And so the point being, there's a movement now to develop rulers, to develop wavelength fiducials, precise ones in the near infrared. And uranium neon's one. And so what we're going to go through now is what's coming in this field and what we should all be getting really excited about. One of them is espresso on the VLT, and that's coming going to be next year to 2018. This is the real near future for radial velocities. And if we look at espresso, we see that it's optical near infrared. So we've got the VLT, remember, or to say, is 4 8-meter telescopes. And they can work either individually or they can work in unison. And espresso is going to take advantage of that. So with espresso, we can be looking for planets either on individual 8-meter telescopes, radial velocity, or we can combine all 4 telescopes and go a lot deeper and have essentially like a 16-meter telescope. Not at the same resolution. So espresso will have a resolution over 100,000 resolving power, but if we combine the 4 telescopes, then we decrease to about 60,000. That's a lot of desensitivity loss, but we can still do precision and radial velocities with that. So I said HARPS, PFS, they've been the kind of standard bearers in the optical now. They're the 1 meter per second, sub 1 meter per second instrument. So gains over that are something like 2 to 3 magnitudes in depth, and crucially, 2 orders of magnitude increase in RV stability, few centimeters per second. And so the question is, well, how do they do that? And we'll come to that in a slide or two, because that's the key. Remember what the Earth is around a sun-like star in the habitable zone? It's 9 centimeters per second. You need 2 or so centimeters per second to statistically detect that. 3, 4, 5 sigma. After espresso, well, in the I'm going a bit further here, and this is important being in Brazil to bring this up, that there's high-res coming for the radial velocity community. So what we're trying to do with high-res, well, if we look at that, it's a factor 6 increase in collecting area, which means originally when it was called codex, we could look at the sample and you can basically sample a billion objects. Depends what you want to do with that. It doesn't gain in stability over espresso. It was proposed to gain in stability over espresso, but then we figured out that espresso can actually reach 2 centimeters per second or so, because that was the original science case for high-res, or the engineering case was to get it to 2 centimeters per second. It was called codex at the time, so I've showed the two papers here you want to go look at. It will be called codex when it's Pasquini, and it's now high-res and Myelino. And the science driver for this is actually to look at the exoplanet atmospheres then. So if we don't gain in RV stability over espresso, it's difficult to make the case to do a radial velocity search for planets if we're not gaining in RV stability. We gain in depth, but remember this is a 40-meter telescope. And RVs are an expensive way to find planets. So to gain the time, you can't make the science case, it's really hard. So the case here is though exoplanet atmospheres, and habitable zone ones orbiting M-dwarfs are going to drive this field as well. Remember, this is also over 100,000 resolution. So studying exoplanet atmospheres at super high resolution. This will be really exciting. How do we get to 2 centimeters per second, or 1 centimeter per second? And the way we can do it, or the way it's going to be done, is basically using a laser frequency comb. So this won the Nobel Prize for Physics in 2005. And the idea is basically to couple the laser frequency comb to a highly stable spectrograph, like espresso, like high-res, and for the time being, like HARPS. So this is being employed on HARPS to significantly increase the stability of HARPS. Remember, HARPS was only ever developed to be 1 meter per second. 1 meter per second stable. That was what it was developed to be. Already, I showed yesterday, we can detect signals at 20, 30 centimeters per second. So HARPS is doing damn good in stability. It's approaching the thorium-argon limit. So remember, the thorium-argon limit is 20 centimetres per second. We can't do better than that on HARPS. But maybe if we replace the thorium-argon with a laser frequency comb, we can do even better, even on HARPS. We maybe already have an instrument with more development that we can get to the few centimetre per second limit. Well, that's to be argued. But you can see here, this is a thorium-argon spectrum. This is the point. This is the observed thorium-argon spectrum across wavelength. So this is wavelength increasing over one order. Remember, I showed the orders from the shell spectrum. Look at the laser frequency comb spectrum. So what you get is basically this pulsed laser. And this pulsed laser, and if you can delay that pulsed laser and stabilise it, because this is what you've got, all of these laser frequencies. If you can deal with those laser frequencies, stabilise them, and shift them into the optical, this is what you get. And this is basically, this is a dream. This is the perfect wavelength ruler. And this is what will get us to 1 centimetre per second, these femtosetting mode locked lasers. So that's what you're trying to do, lock the modes. And it's been done on HARPS already. Still problematic. For instance, there's crystals, there's these photonic crystals here that have very short lifetimes. Things like that are delaying the problem, delaying the development, sorry. For instance, those crystals now, they've got them to like 900 hours, and that's something incredible. But it's 900 hours, it's not a long time, you need to replace it. So, but they've looked using the laser frequency comb. This is just one shell order, the centre of the HARPS detector, order 42. And you can see this is scatter, essentially, where you've got these big drifts from the residuals of this, in this case it's a 4th order fit to the thorium-argon. And you compare that to the laser frequency comb that you get. So the wavelength from the laser frequency comb. And then you start, this is the difference plotted here between the two. And this is quite cool, check this out. These jumps, you're actually sampling the stitching pattern of the detector. So the detector, the CCD, is made up of little chunks that are put together. And right at the boundary of those chunks, the pixels have just a very, very small difference in size. And when you look at with a laser frequency comb and compare it to the thorium-argon, you actually see the jumps in the detector. So you're actually sampling the stitching pattern of the detector now. This is pretty cool. And when you look at and extrapolate just on HARPS, from the HARPS data, you compare it to the thorium-argon and HARPS. So now, thorium-argon, this is the photon noise limit. It starts to deviate from the photon noise limit at 10 centimetres per second. We said 20 before, 10 centimetres per second, something like that. When you include the laser frequency comb, then you deviate down at the 2 centimetre per second level. So this is already validating the fact that this design, using this pulsed laser, is going to deliver 2 centimetres per second. Okay, continuing, I said we've got a method now to reach 2 centimetres per second. So we're down at the centimetre per second limit. Now we're in the regime where we can detect exoearths around sun-like stars in the habitable zone. That's the regime we wanted to be in for a while. Now we've got a pathway to do it. So there's things like the Habitable Planet Finder, and this is being developed at Penn State, that's trying to develop this in the near infrared and use a laser frequency comb in the near infrared where it's a bit easier to deal with the pulses and generate the spectrum, the calibration. But they have problems in the near infrared a bit with modal noise, even though, remember, the number of modes decrease with wavelength. So they've been working on that quite heavily. And this was the project that I was working on as a postdoc, but it changed, we lost all the money. It was supposed to be the Precision Radio Velocity Spectrograph, now it's the Habitable Planet Finder. I believe it will go on the HET telescope in Texas in a couple of years' time. But this is aiming at 1 metre per second at least precision in the near infrared. So this will open up a lot of M-dwarf For M-dwarf surveys, this will be excellent. A 10-metre telescope and a near-infrared, where all the flux, remember, of M-dwarfs peaks, the J-band. And so this will be us at 1 metre per second, radial velocity stability in the near-infrared. This is an M-dwarf machine. Remember though, optical near-infrared, we get a much better confirmation of Doppler signals if we can confirm they've got the same peak, the same model. So Carmenes is like a European version of that. But Carmenes is going to use both optical and near-infrared, both at 1 metre per second. And Carmenes is already taking data. Carmenes is on Sky. It's not in the 1 metre per second level yet in the near-infrared. It's 1 metre per second stable-ish in the optical, but it's not in the near-infrared. This is kind of HARPS, basically, in the optical near-infrared. It's vacuum, remember, it's put in vacuum, it's temperature controlled. So they're working heavily now to get the 1 metre per second stability in the near-infrared. They believe it's not far away. They understand where the systematics are, so that's cool. But just to say, this is taking data now. We're now getting to the point, close to the point of an instrument 1 metre per second in the near-infrared. So, let me change tack a little bit. I've been talking on about radial velocities. So let's quickly move to photometry, because radial velocities and photometry have already been going hand in hand for the past 10 years or so. Or in fact since 209458b was discovered in 2000, so 16 years now. And what we want is more, and we want astrometry to come along and join that fate, and we want direct imaging to join us as well. But where are we going photometrically? Well, from the ground, the next method, or I should say the next mission that's coming along, is the Next Generation Transit Survey. And that's also currently operating, but not operating at full capacity. It's 12 cameras, ground-based cameras, and this is in Chile as well, ISO, Paranal. And the point is that the cameras are sensitive in the red optical. So these are red optimized cameras, which are good for K and M dwarfs. And the point here is to actually build up the population of transiting Neptunes around nearby stars. That's the science goal, is to get into this kind of Neptune regime, which is, for nearby stars, is pretty underpopulated. And we've seen from Kepler, there's a huge population of these, or the kind of super Earths moving into icy giants. So the next NGTS wants to detect Neptune. So just know that there's a kind of red optimized survey coming online, or it's operating but is going to ramp up soon to build up the population of Neptunes. So for people that's interested in atmospheres, that's an interesting project to keep an eye on. Now moving really away from anything I do, is JWIST. So we're getting into space now. So JWIST is looking at, I had here before 2017 time frame, 2018 or so, where that's underestimated or whatever, I'm not sure. But the idea for JWIST will be to really now start to probe the atmospheres of exoplanets. So you can see the JWIST bands here. We've got a spectrum of a probable or an exoplanet, and its relative flux, it's SED. And so the idea is that we can start to probe these big bands of features and characterise super-Earths in particular. And so also direct imaging can be done with MIRI at mid-infrared wavelengths. So what I'm getting at here is keep your eye on JWIST from the exoplanet side. I know it wasn't one of the real science drivers, but transmission spectra of super-Earths and potentially directly image young planets. Furthermore, on the European side, there's KOPS, and maybe people's not heard as much about KOPS. KOPS is a mission to follow up radial velocity planets from space. So KOPS is going to be a directed mission in the sense that they take the radial velocity detected sample and follow them up to look for transits, basically. That's the KOPS from space. That's the KOPS mission goal. So this has got a time frame as well, similar to JWIST. It's the next couple of years coming up. But this will be really interesting for old planets, because we get that continuous cadence from being in space, essentially, and really high precision from being in space. And so this will be excellent to follow up the RV detecting the really nearby objects. That's the goal. Probably one that everyone's heard about, I would think, is TESS. And this just becomes ludicrous to me, but anyway. TESS is going to do kind of Kepler type analysis of bright stars, bright nearby stars. Not with the same cadence as Kepler. Remember, we've seen the talk on Kepler where Kepler just focuses on one field of tons of stars, a couple of 100,000 stars, and looks for planets in that, or transit events in that little window over 5 years or so. Now K2 is a bit different, but the main Kepler mission. TESS is going to do something else. TESS is going to observe with you'll get a full cadence of all stars, the whole sky, out to about 30 days or so. So it'll be complete out to about 30 days for the whole sky. But because of its observing pattern, that you can see are these kind of blocks, the way it's going around the Earth and it's kind of observing up, covering these strips, these bands. When you get to the poles, you get about 365 days of coverage. So TESS is going after, like the Earths and the super Earths, and when we look at the predictions for what they're going to detect, I mean, it becomes like giant planets. Upper limits were predicted here. That's 17,000. These are bright stars. And they're predicting 3,000 sub-Neptunes and things. I mean, this is ridiculous. I mean, the kind of follow-up we're going to have to do on these objects will be mad. But, yeah, look out for Kepler. 2018 time frame, but I think didn't one of the... I shouldn't laugh actually, but didn't one of the rockets explode as it was being filled with LO2, I think, so in a test, and one of the rockets that are going to be used by TESS, because it's going to be launched privately, so I think it might be delayed, but kind of 2018 time frame. Going further ahead, now we get really interesting. Is Plato 2.0 mission. It's a European mission. This is going to really be, or supposedly be, kind of Kepler for all stars, all bright stars. So Plato is going to have 34 small telescopes, but 12 centimetre telescopes in space, 136 CCDs to get 50% sky coverage. So we've got 1 billion stars again. This is like the second or third time I've got 10 to the 9 stars in here. That'll be surveyed in the mission. 80,000 masses and ages through astroseismology. Remember, we talked about astroseismology, the non-radial pulsations of stars. 80,000 masses and ages from astroseismology. Look at the V-band. That number, 4. We're talking about naked eye stars. Plato's going to do naked eye stars. 3-year mission. And the point is that we'll get out to the 1 AU limit of sun-like stars, bright sun-like stars. The idea is that we can have 3, for systems we'll have 3 transit detections of Earth, radii, planets in the habitable zone of sun-like stars. Also look at the time frame, 20 to 24. It's exactly the same time frame, similar time frame to the ELT. So you'll have high res on the big ELT coming online at the same time as Plato, detecting all these kind of Earths in the habitable zone. So for studying, not only confirming planets, but studying atmospheres and stuff, this will be a really exciting time. So keep your eye on Plato. It's going to find the real exo-Earths on bright stars, on the nearest stars. They need to be confirmed by radial velocities. Okay, so to finish up, what about direct imaging? We've said this is kind of where we want to go. And so if you can simulate Earth-Sun systems. This is from Casting et al., showing a kind of Earth-Sun system. And also looking at exozodies, or exozodiacal light, noise, essentially, sources from what we've got just rummaging about in the solar system, for instance. And so you can perform population simulations, essentially, of what we expect to kind of have as far as contrast, planet-star contrast and flux and projected separation. And we want to be kind of, at least in this regime, it's a bit difficult. But that's where we are as far as Earth's 10 to the minus 10 in contrast. That's where the rocky planets exist. So remember that's contrast of about 10 to the minus 10 and less. Because we want to be a bit further away if we want exo-Earths around Sun-like stars anyway. And so the question is, how do we get to 10 to the minus 10 in contrast if we want to detect exo-Earths? And below, of course, because we've seen that the further away they get, that contrast increases, the amount of reflected light decreases on these objects. Well, I didn't know much about this. Marcel, I think, asked me about METIS, was it yesterday or the day before, so I took a quick look at METIS and see what it does. And here's some of the predictions from, this is going on the ELT, by the way, so this is again, it's going to be one of the first instruments to be attached to the ELT, 2024, 2025 time frame. So this will be a high resolution integral field spectrograph. I mean, 100,000 resolution IFU, or IFS, sorry, that's pretty impressive in itself. Running from about 3 to 5 microns mid-infrared. Medium resolution at 5,000 long slit spectroscopy. And so you can see if we look at distance against kind of flux density, this is kind of the 5 sigma detection limit of what METIS thinks it will get. And if you look at this is 1 radii Earth, by the way, at 3.6 microns. This is an optimized solution, but as a function of temperature, it depends on the temperature of the planet, of course. Then for G, K and M stars, you can start to probe if they're nearby. Okay, we're talking 4 parsecs away, we're talking the nearest stars. You can maybe start to detect hot planets, hot small planets of 1 Earth radii. Of course, this is optimized solutions, but check out, there are 2 papers on this, Brandl and Kwans. From space again, there's W first, that will fly, again, 2025 time frame is the last time frame that I was able to check out last night. And this has a coronagraph. So W first will have a coronagraph in space. Remember, talked about the coronagraph, you can put your thumb up, block out the streetlight. This is going to do that. It's going to block out the starlight, suppress the starlight straight away and have a coronagraph in space. And now we're getting really cool, because now we get 10 to the minus 10. Should have a minus in here. 10 to the 10 in contrast. Now we're approaching now we're at the rocky planet regime. So I say Neptunes are accessible. Probably some rocky planets might be accessible. These rocky planets fairly near to their star. They can't be too near. You've got a coronagraph in the way, so you've got an inner working angle issue there. So that's one of the problems with W first, or one of the issues for any coronagraph, is how close you can get to the star in angular separation. And this is what the coverage that W first will get, that they'll definitely get, and this is more speculative in the dotted lines. The colour is just a function of mass, it's log Earth masses. But you can see then you can start to probe into the super Earth regime, get into the rocky planets at 10 to the minus 10 contrast. They're also planning to do, so you can do atmospheric studies with W first, but they're also looking at microlensing, and I wrote this in because we discussed about free floating planets. They're expecting to detect a lot of free floating planets coming on to understand the dynamics of the early systems and the formation mechanisms. So this is really excellent mission to look at. To finish up, what I would like to see, and what a lot of people would like to see, would be interferometry in space. And I'm going back a few years now. This was, maybe even before the year 2000, this was proposed. So first was terrestrial planet finder. Then, and this is a US mission, and then there was proposed Darwin from the ESO side. And the ideas were to put nulling interferometers in space. So kind of fly formation craft in space and use interferometry to null, basically get rid of the star interferometrically. And what you can do when you do that, simulations were showing that you could then directly image the planets. I mean, directly resolve the planets and also take spectra of them. And I'm talking about Earth's in the habitable zone of Sun-like stars now, completely. This is what we wanted. Sadly, as happens a lot, funding gets in the way, and both of those missions got cancelled. And as far as I know, there's no, I don't know if you know, Fred, if there's still any push to revive TPF, or I don't think so either. I haven't seen much for Darwin either from the European standpoint, which is a shame. But so in the last slide, I just wanted to show you that we haven't stopped there at 10 to the minus 10. We're pushing even further. And so there's already tests underway. This is not a mission that's going to fly anytime soon. This is a simulation. But these tests are underway. We're looking at coronagraphic missions in space, but using shaped pupils. So not just a circular coronagraph, shaping them and apodizing. So this is called apodized pupil LEO coronagraphs to get below this 10 to the minus 10 limit, but at low inner working angles. That means you can get really close to the star, which allows you to look further away and capture these kind of exo-Earth systems. This is a simulation of the solar system. If it was put out at, I think it's 10 parsecs. And what you see, 5 or 10 parsecs, and what you can see now, under these tests, of course optimized tests, with these shaped pupils, if they're on a 12-metre telescope or so in space, you end up with about 13 detectable exo-Earths. So you can detect the solar system. Fairly easy. I mean, even Venus. You can get really close to the star with these coronagraphs. So you could detect Venus, in this case, Earth, and there's Jupiter, stonkingly bright. 4.5 gigayears old, remember, really faint. So, just to let you know that even though space interferometers have kind of been mothballed now, not mothballed, they've been abandoned, there's still projects on, at least being envisioned, where we can put coronagraphs in space. There's one WFirst coming, and there's others potentially that could give us real images and spectra of exo-Earths quite readily. So, just in summary, we've looked at some of the key, over the 4 classes, we've looked at what it takes to detect exo-Earths. Main focus on radio velocities. Kepler's already done it for stars far away. We're trying to do it on the nearest stars. We've got big databases of radio velocities to take advantage of. And that's how we'll get, I hope I've convinced you, we're already basically approaching the Earth limit around M dwarfs in the habitable zone. We're already getting there. And the goal is to get that on Sun-like stars. This is if the kind of look at habitable planets, if you're just a planet searcher. This is from this Planet Habitable Laboratory in Arizona, and they did do these lovely, nice graphics of, in this case, it's potentially habitable planets ranked by distance from the Earth. So of course you've got Proxima B, and I showed you we also detected Captain B, we detected 667C, etc. There's also, I never mentioned it, and I maybe should have, there's another interesting planet, Wolf 1061C, and that was just recently discovered this year by a group in Australia. And this is a 3-planet system, 3 small planets, and one of them, it's a few Earth masses, 4 Earth masses or so, minimum mass, it's radio velocities again, 4 Earth masses, minimum mass. Slap bang in the habitable zone. So Wolf 1061C, go check it out if you're interested. And then you've got all these nice Kepler systems come in. It was discussed 186F, and so you've got a few others from Kepler. Can I just show a video if it works? And I'm happy to take questions at them now if you like. But So this was done by one of my grad students for Proxima B. So you've got Proxima B, and this is the Proxima Centauri, Alpha and Beta Centauri. And this is what he did with Blender, which astounded me, to be honest. This is just coded in Python through Blender. And so this is what we envisage. So we tidally locked the planet, which you can see now, it's starting to be illuminated by Proxima Centauri. Of course we gave it some clouds, it's got an atmosphere in our minds. Tidally locked. And then we see it whizzing away, and we'll come up and we get a look at the system habitable zone from this. I'm happy to take questions of that, by the way. I'm finished now. This is all just excess. But so we can see now that we swing through the atmosphere of Proxima Centauri itself, and there's the orbit, a plan view of the orbit and the habitable zone. So that's what the system looks like, a little bit of eccentricity. And that's the kind of boundary of the habitable zone. But yeah, I wanted to show this for a couple of reasons. One, if you're interested in public outreach or so, Blender is an excellent tool, especially if you can program it through Python. Done this in a couple of weeks. Impressive. Yeah. Blender, yeah. And from that, that's his Ricardo Ramirez. From that, you can make these nice images from Blender. So I'll just leave this up now and take any question. I should say that we have a astrobiology conference. It's an IAU symposium next year in the south of Chile, in Coyhaique. So put this in your calendars, November 26th to December 1st, Coyhaique, south of Chile. Lovely, lovely part of Chile, very green, lot of lakes. Nice time as well, November, December. But this is the astrobiology symposium, the IAU symposium. So you're all invited to come to Chile and have a good just before Christmas discussion. Thank you.